many grams?
No, you said how, you just said how many, do you mean grams? You said how many hydrogen?
How many hydrogen?
You mean grams?
How much hydrogen also, yes.
Huh? It's open-ended? Okay. This is a good question because it's a straightforward stoichiometry problem. So we'll take a look at it. You have 23.2 grams of nitrogen. What's your first step?
Put it on right.
Got to change it to moles. So 1 mole of nitrogen is 28 grams. So we do that division and get
0.827. Yeah.
8.27, close enough,
Um,
moles of nitrogen.
mhm.
And then we're asked for ammonia. So the next step is to relate the moles of nitrogen to the moles of ammonia. So our ratio looks like moles of ammonia to moles of nitrogen. And where do those numbers in that relationship come from?
The equation.
From the balanced equation. And so it's 2-to-1. So that tells us that we have 1.654 moles of ammonia. But we're asked for grams of ammonia specifically, so we have to multiply by 17 grams for 1 mole of ammonia, and we should have our answer. Which, I don't know what it is.
So that would be, well, we finished, we did all. What do you get in there? 28.15.
How much?
28, well, 28.15.
Okay. And then to do the hydrogen, we've actually got some of the work done already. We can use the moles of nitrogen, so we can just jump to this step and save that amount of work. And now we are looking for hydrogen, knowing nitrogen. And where do those numbers come from?
Equation.
And what are they?
3.6. 1.31.
Yeah, a little different than 6, but the same part of the number line, I guess. So, doing that, we get what? 1, 10 times 3, 21, 6, 8, 2.48 moles of hydrogen. In which case we could stop because it was just asking us how much hydrogen. Didn't say moles or grams, and this is an answer. Or we could go 1 step further and get 2 grams of hydrogen for every 1 mole and get 4.962 grams of hydrogen.
So those numbers in grams, that would be right too.
Sure. I mean, to answer in grams, you had to have moles first anyway, so.
Yeah.
And if it asks for grams, you have to answer in grams. But otherwise, you can do it either way. All right? Piece of cake.
Not piece of cake.
I want to drop back a second and talk about something that I didn't talk about when we were talking about chemical reactions, because I didn't have my stuff with me. But I want to talk about an aspect of chemical reactions that's always there, and that is that there's an energy term to chemical reactions. Now, we did the pop bottle in here, right?
Mhm.
We blew up a pop bottle, and you know that there are reactions that give off energy. And we have terms for that. If it gives off energy, we call it exothermic reaction. If it's a reaction that takes on energy or absorbs energy from the surroundings, then we call it endothermic. The way to tell these is to check the surroundings. The surroundings will get warm if something is giving off energy. The surroundings will get cold if it's something that's absorbing energy. So I brought a couple of demonstrations that I thought we could use in addition to the pop bottle. that would show this process. This is a solution of sodium acetate. Sodium acetate is a salt, and it dissolves in water, and it dissolves in water quite well, but it's very temperature dependent. If I heat this solution up to a high temperature, 80 degrees, 90 degrees, or almost close to boiling, lots and lots of sodium acetate will dissolve. Now, we haven't done solutions yet. That's an upcoming chapter for us. And when we get there, what we'll find is that we could create what's called a saturated solution. And that's a solution that has dissolved as much stuff as it theoretically can. It can't hold anymore. If I heat this up, it dissolves more. But then when I cool it back down, theoretically, what should happen? If it dissolved more when it was hot, and I cool it back down to the point where it can't hold that much stuff, it should
Release it.
It should give it back. It should form a solid. It should form a precipitation. But sometimes, and sodium acetate does this particularly well, we can trick the solution into not giving it back. And it forms a situation called supersaturation. In other words, right now, this solution contains more dissolved solid than it theoretically can under these conditions. Now, I'm going to precipitate it out by putting in a seed crystal. I have a little bit of the stuff right here. I'll put it on the end of a stirring rod, touch the top of the liquid, and that will cause the precipitation to occur. And when I do, I want you to be impressed that there's an energy factor involved. So we need a few representatives to feel the flask and tell the class that it's room temperature.
Room temperature.
Ah, girl.
Temperature. Room temperature.
Okay. I'm going to take the stirring rod, load it up a little bit with some solid, and then sometimes just removing the cork is enough. A piece of dust might fall in there, give the thing a surface to form on. Sometimes not. So we'll take a look. Doesn't look like it. I hope this is the right flask. And if I touch, oh, there it goes. The precipitation began. Perhaps a particle of the stuff fell off the stirring rod or a piece of dust fell in there, and it has now precipitated all the extra sodium acetate that should not have been dissolved in that solution at this particular temperature. This supersaturates so incredibly well that it appears as though there's no liquid left in the flask whatsoever. In fact, it's like a snow cone. It's kind of mushy and wet. If you were to squeeze it out and get the drippings, you would have a saturated solution of the sodium acetate. But feel the flask.
Well worn.
Warm.
Is that not rock candy?
Rock candy?
Rock candy?
Wow.
No. Yeah, and it's a slower process than this, but along the same lines. What you're doing is slowly letting the water evaporate so that it will not stay dissolved and will come back as rock candy. Now, can you think of a practical application of this? Yeah, there you go. Commercial hand warmers. They sell them as little pouches of the stuff. And inside is a little metal disc that when I snap the little metal disc, the precipitation will begin. Right now you can see the bubble at the top that there's a liquid inside. And if I snap that little disc on the inside, you can see the precipitation taking place throughout the little pouch, and it is re-solidifying. It's actually unsupersaturating, and again, you've got sort of a mushy solid here. But this actually gets warm, and we can pass it around. It'll stay warm for maybe 30 minutes or so. So if you've got one of these, you can take it to a sporting event, and when your hands get cold, or a camping event, you can trigger it and it will undo the dissolved sodium acetate and become warm for about 30 minutes. They tell me that they sell big ones for sleeping bags that you can probably burn yourself with if you're not careful.
Does anything happen with this little instant, like, you know, they market these little drinks to where if you need to, if you press something and it will heat it up instantly.
I doubt this is it. This is a food-grade substance, but I think it would have to be contained. It's not something you want to necessarily ingest. But there are other ways to make hand warmers. The key would be, is it redoable? Can you redo? Or is it a one-time shot? If it's a one-time shot, then it's probably a different chemical reaction. The nice thing about these hand warmers is that they're reusable. All I have to do is take that back to the lab and pop it in boiling water for about 6 minutes. It will redissolve and then let it cool back down to room temperature, and I have the pouch ready to go again, and it can be used as another hand warmer for another time.
So
They
when
don't
you're,
last forever, but they last for quite a few trials.
so when you're doing the little snapping action, is that like that's releasing some type of metal?
No, what it's doing is it's causing the precipitation to begin. We don't understand precipitation extremely well. We're not sure why this stuff supersaturates and why doesn't it come back. It somehow has a difficult time doing that. And for some reason, the little metal disc snapping is enough of a perturbation to the system that it causes the precipitation to begin.
Wow.
And once the precipitation begins, as you saw with this one, it's going to happen throughout the entire solution.
So that's not the same as the kind you get in the store that, friction causes to.
You can buy these in the store, but there are other kinds that you can buy also. And the key is it reusable? There are kinds that once you break the opening of the package, the air, oxygen gets in, usually with an iron, finely divided iron sample, and then it actually rusts, and that rusting is exothermic and it gives off heat. But then once it's done, you have to throw it out. There's no redoing it, reusing it. So that's a problem with that. Now, I brought another one that is just the opposite. This is an exothermic reaction. This one is endothermic. So again, we need a couple people to feel the flask and say it's room temperature. Yeah, room temperature, good. Okay, this is also an extremely rare chemical reaction because it's a reaction where two solids react together, and that normally doesn't happen. Normally, you need to have something that gets the materials closer together, and in the solid state, it's usually not enough. For example, my hand doesn't react with this table. Good thing, because if it did, all of a sudden I'd be stuck with the table, but it just doesn't get close enough to the atoms in the table to actually make some kind of chemical reaction occur. But this is a very rare reaction in that I have a flask that's filled with a solid material and a vial that's filled with the solid material. So I've got two piles of solid, and when I put them together, what do I end up with? Well, some people say one pile of solid. But if I give those two a chance to just interact with each other a little bit, give them a bit of a mix like this, what we're going to find is that it's actually going to turn into a liquid. The chemicals are, you ready for this?
Yes.
Ammonium thiocyanate and barium hydroxide octahydrate.
Oh,
And so I knew you wanted to know.
that makes sense now.
The hydrates are compounds that have water locked in their crystal structure. And what happens here is it just releases those waters and they become part of the liquid. But you can see what also is happening to the flask. It's ice cold. That's frost that's on the flask. You can pass it around.
It was barium what? I'm sorry.
Barium hydroxide octahydrate. So that is technically a way that a paramedic's cold pack could work. That is not the stuff that they typically use in cold packs, but it's the same concept or idea. In cold packs, I think they have a salt, something like potassium nitrate, which when dissolved in water, they break the opening between that and the water solvent, and when it dissolves in water, it absorbs energy and becomes cold as well. Yes, ma'am.
So, could the first one also be endothermic when you boil it and then it goes back into?
Well, I guess you would say that the
Waterfall.
dissolving process is an endothermic process because I have to supply heat for it in order to do that dissolving at the higher temperature, yes.
Okay.
But then it reverses when we do it in the classroom and it's exothermic to give off the heat. Okay. Yeah, question? Supersaturation is actually in a future chapter of ours, but I'll give it to you. It's the dissolving of a substance into a solvent to the point where it is dissolved to a greater degree than it can.
Do we need to know?
Not yet.
I mean,
We will eventually. And so it sounds like magic because we're talking about it existing in a state that it's not supposed to be in. And that's exactly what a supersaturated state is. It's a state that it's not supposed to be in, and that's why it's so easy to get it to come back into the other state. Okay? Back to stoichiometry then. So we've looked at stoichiometry, we've looked at limiting reagent, we've looked at all these things, now we just have to put it to use. So let's try to do a couple of examples today.
can you go over names already?
Sure. How about we do it with an example? Name the first molecule.
Iron oxide, ferrous oxide.
Close.
Iron 3 oxide.
Iron 3 oxide.
Yeah.
Which would be ferric, if you were using the old terminology. Okay. Name the second component. Oh, too easy. So here's the question. How many grams of iron are produced by reacting 30 grams of aluminum with 130 grams of iron 3 oxide? Go.
Have we went over these?
Say what?
Are you really gonna write the answer really, really tiny?
Yeah. That way you have to get up to look at it if you want to check your answer.
Great.
Have you, obviously I was told how to do this when I was majoring around outside.
Well, we did this last couple of class meetings.
I've been losing that, but I am getting taller. I was up 3 this morning, I got it. Yes.
You got something. I'm not sure what you got.
I got
All right, well, give this a try. Done already?
Okay. No. I was. So this. What else? Right,
Okay, if I ask you this, can you do a stoichiometry problem?
Yeah.
Could you do one? Could you do two? Okay, that's all I'm asking you to
Come
do.
back to the
Two
last.
stoichiometry problems. One stoichiometry problem is, how many grams of iron can you make from 30 grams of aluminum? Period.
None.
And then the second one is, how many grams of iron can you make from 130 grams of iron 3 oxide?
You can't make any from them.
Oh,
You know
but
what?
can. According to this reaction, you can.
All I know is look at the periodic table.
So when I do these, they
Okay.
you put them together.
Well, you do the two separate things, and then we're gonna pick the smallest of the two as our final answer.
Why?
Because in the limiting reagent business, remember the cars in the automobile factory, we had 10 car bodies, we had 32 tires. What happened? How many cars can we produce?
I think I'll be going to the.
Only 8, because once we put the 32 tires on 8 vehicles, we were done. We have no more tires. So it limits the rest of the reaction from taking place. So the limiting reagent is the one that produces the smaller amount.
So it produces a smaller amount because of
Because it runs out.
it produces a smaller amount of product.
A product, yes.
Okay, am I sensing that maybe we're a little rusty here? And
Yeah.
should do this one together?
Please. Yeah, we should do a couple together and then you should talk about ourselves.
Okay, So what would we do? What we have here proposed to us is a limiting reagent problem. How do I know that? I'm given two starting amounts. And the two starting amounts say 30 grams of aluminum, 130 grams of the iron 3 oxide. Is there any guarantee that both of those are going to react exactly equal perfectly with each other?
No.
No. What's much more likely is one of them is going to run out. And when one of them runs out, the reaction will stop because there's no more fuel to run the reaction. And so what I'm going to do to answer this question is I'm going to perform two stoichiometric calculations. One, I'm going to answer the question, how much iron can I make from 30 grams of aluminum? Period. Straightforward stoichiometry problem. The second one is, how many grams of iron can I make from 130 grams of iron 3 oxide? Those are two separate problems. Once I get those two answers, I will look at those two answers and I will pick the smallest of the two as my final answer. Because that means that substance must have been the limiting reagent. It ran out after it made that much substance, and so no matter how much of the other substance I have, I cannot make any more of the product.
Is it the iron 3 oxide 0.81 moles?
I don't know. We have to do it. So let's start with the first one, which is 30 grams of aluminum. What would my first step be? Convert to moles. So 1 mole of aluminum, about 27 grams from the periodic table. So that looks like what? 1.11
Yeah.
moles of aluminum. Okay? Well, I'm just going to continue with this stream, and I'm going to calculate how much iron this could produce. So I set up a ratio, a mole ratio, that says I'm looking for iron. I know aluminum. Now, what's the ratio between those two guys, and where does that ratio come from?
From the
2
comes
moles.
from the formula.
It's from the balanced chemical equation, and it's 2
Moles of aluminum.
to 2. Okay. 2 moles of iron, 2 moles of aluminum.
Mm.
So, heavy math, I might need my calculator. I get 1.11 moles of iron that are produced. Okay, I'm going to be happy with that for a minute. Let me go on and do the second calculation. If I have 130 grams of iron 3 oxide, what's my first step? Change it to moles.
You forgot to convert it to grams.
I don't need to yet. I'm not going to do any more than I have to. So I am plain student, okay? I'm not going to do any more than I have to. I'm only going to do what I have to, so I'm going to leave it in moles for the moment. So how do I change this into moles? 1 mole of iron 3 oxide is, oh, I don't know. Okay, so over on the side here, I know that it's 55.8. There's 2 of them. Oxygen is 16, there's 3, that looks like about 48. So that's 16, 10, 18, 19, 10, 159.6.
Sounds good to me.
Me too. So 130 grams at 159.6 grams per mole would give me
Zero point eight one
0.81. Is that enough?
four.
4 moles of iron 3 oxide. But I really want to know how much iron can I produce, so I set up a factor. This time it looks like moles of iron, because that's what I'm looking for, over this time moles of iron 3 oxide. And what is the ratio between these guys?
2 to 1.
2 to 1. Where do those numbers come from? Balanced chemical equation. So this tells me I can make 1.628 moles of iron. Now in truth, I can't make both of these, so I'm not going to add them together. I can only make one or the other, and the theory is I can only make the smaller amount. So that must be this guy here. That means aluminum was my limiting reagent. It's the one that's going to run out. And I am asked for grams, so now would be a wise time to change this to grams. And I can do that by saying, well, there's 55.8 grams of iron in 1 mole. Where'd that number come from?
Wait, I want,
Periodic table.
the top number, 1.11 came from the aluminum, right?
This top number?
Yeah.
Well, it came from this calculation,
Okay.
with moles of aluminum changing it into moles of iron.
Okay,
So this is actually moles of iron now, not aluminum any longer.
okay, you said your limiting reagent was the aluminum.
Right. And so I'm gonna change that into grams, and the final answer is
61.93.
61.9 grams of iron. That's right.
Will there ever be a time for you to pick a bigger one?
No, I don't see why. Because that's really a fictitious amount. All right, since the limiting reagent runs out, there's no way we can actually make that amount ever. It's a fantasy number. And we do it just to see which one is the smaller of the two. So 61.9 would be my answer. Okay. Questions? One interesting follow-up question to this would be, okay, how much of the non-limiting reagent is left over? If it's a non-limiting reagent, what are we saying? The limiting reagent, how much of the limiting reagent is left over?
No.
None, it runs out. But that means the non-limiting reagent did not run out. So could we calculate how much non-limiting reagent is left over? First of all, what is the non-limiting reagent?
Aluminum.
No,
Aluminum.
it's the iron 3 oxide. The aluminum we decided was the limiting reagent. So what would I need to know in order to determine how much was left over?
Exchange 1.6 grams and subtract it.
That's a good theory, except that this is moles of iron, not iron oxide.
You need to know how many grams are produced of iron 2 or iron 3 oxide.
But I'm not producing any iron 3 oxide, I'm using iron 3 oxide. So I don't want to know how many grams are produced,
How many grams were
Do you
there
need to know
originally?
the aluminum?
how many grams were not there originally. Yeah, that's what I'm looking for, how many grams are left over. How am I going to find that?
How many grams were initially there?
I know that, 130.
Use the
130 minus
130.
61.
No, because this is grams of iron. That's iron oxide.
So then you use the gram from the iron.
You change that to grams and you
Change what to
subtract
grams?
the
Change
one
the
point
0.814.
six two eight minus,
So yeah.
and then you
grams.
subtract it from 130.
Okay, then if I change this to grams, it's gonna be 130,
No,
because
not
I'm just
that.
reversing this calculation.
1.628.
That's iron.
Oh.
1.628 of iron.
1.628
Right.
God, just tell
Can
me.
you
Yeah.
tell us?
But
I know,
that's,
instead of-
that's how much iron you use.
If I change this to grams, I've got grams of iron,
Got that.
okay? But it's grams of iron that I couldn't possibly make, because it's not the limiting
So you
reagent.
have oxide left over, correct?
Moles of,
I'm gonna have some iron oxide left over, and I want to know how much.
the 1.68 iron from the 1.11 moles of aluminum.
So you subtract the 2 moles. You
I
subtract
don't
one.
think that'll do it, because,
So what's the answer?
well, I'm trying to get you to think logically. Okay, what if you went on a shopping spree? And I said to you, how much money do you have left over?
$3.
What would you need to know in order to calculate that?
How much you spent?
How much you spent
How much you started out with?
and how much you started out with.
So you subtract
Okay, we know how much we started out with. What don't we know yet?
How much you left over? How much you spent?
How much we spent. How much did we use? If we know how much iron oxide we used, Then we could subtract it from this and find out what was left over. How do I find out how much iron oxide I used?
Convert 0.814.
Well, I now know how much aluminum I used. Can I relate aluminum to iron oxide? I related aluminum to iron. I can relate aluminum to anything in this equation. That's the beauty of stoichiometry. Any substance can be related to any other substance. So if I had 1.11 mole of aluminum that I used, I actually consumed, because it's a limiting reagent, then the question is, how much iron oxide did I use? Well, I'm looking for the iron 3 oxide. I know aluminum. What's the ratio between those guys? 1 to 2. Where'd you get those numbers from? Balanced equation. So I must have used 0.555. Does that look right? I must have used 0.555 moles of iron oxide. Okay, can I change that to grams? Sure, I've already got the molecular mass. So 159.6 grams for 1 mole of the iron 3 oxide. This tells me that I have a total of
Goodness. 88.245 grams.
close enough. 88 is good enough. Okay, so if I started out with 130 and I consumed 88, I can calculate what I have left. This is what, 2, 4, 42? 42 grams left over. Oh, too easy.
I got 88.5.
Okay, 88.5.
That was 59.6 grams. To the left.
That's how much iron is left over.
Iron oxide
Okay. Okay.
is left over.
Well, wouldn't iron be contained in iron oxide?
Yes, it is, but they're different chemical substances.
So if you calculated how much iron you produced, okay, I get it now. Not existent, but produced.
I can calculate how much iron I produced. In fact, that's what I did. But remember, not all of the iron oxide went into making that iron. Some of it was left over as iron oxide.
Okay.
And that's what I was asked to calculate.
Can we do another one?
Now we're ready to solo.
No.
Is this like, yeah, the formula for cellular respiration. I think so.
Okay, so here's a problem from the stoichiometry sheet that you'll find on the website. And it tells you that green plants can make sugar, glucose, which is known to us as blood sugar, from carbon dioxide and water through a process called photosynthesis. Uses the power of the sun to have this happen. So carbon dioxide and water react together to make glucose, and they have some oxygen left over. This is actually how we get oxygen in our air. Because if you think about it, we've got oxygen in the air, but everybody's consuming oxygen at an alarming rate because there's so many of us. Where does that oxygen come from? It comes from the green things that continuously produce oxygen for us. So next time you're going to cut down a tree, think twice. It's a friend.
1 bowl of what?
1 mole of glucose, and this is
Uh,
glucose right here. Okay? So, how do I start?
Convert your moles of glucose.
Is that 08 or 06?
No,
Where am I looking?
you got it.
In glucose, C6H12O6?
If you got moles.
You find the grams of CO2.
No, you.
Well, then I'd be done.
You
Find
said-
a.
You just convert
Find
6
how many
moles
moles
of
of carbon dioxide on the mole.
I start
Okay.
out with 1 mole of glucose.
I start with moles of glucose. I've got an easy problem here. I'm not given a gram amount to start with, I'm given a mole amount to start with, and that's what I want. Yeah,
So you already have 1 mole of glucose in the equation, so you just convert 6 moles of CO2.
well, let's do it technically so that the numbers change, we can still know how to do it. Okay, so I have 1 mole of glucose. So how much carbon dioxide is that going to take to make that?
6.
I want a ratio of carbon dioxide to glucose. And what is that mole ratio? 6 to 1, because it comes from the balanced chemical equation. So that tells me that I must have used 6 moles of carbon dioxide.
And then you turn around and grade.
Can I change that to grams? There are 44 grams in 1 mole of carbon dioxide. So 6 times 4, 2, 4, 264 grams of carbon dioxide. I'm guessing.
So this is where you only have to do 1 stoic problem, not 2.
It's not a limiting reagent problem. I'm just dealing with 1 substance.
That's it, right?
Oh, so that's only for the double reactants?
That's my answer. Sorry.
That's only for the double reactants?
It's only if I'm given, and the key is that if I don't know how much is reacting, okay? This says I made 1 mole of glucose. That's a definite. I know that for sure. Now I can use that to relate it to anything else in the balanced equation. In the first problem, I'm told you got 30 grams of aluminum and 130 grams of iron oxide. You don't know which one runs out or how much was actually used. It's a guess.
Okay.
So you have to do the double calculation in order to find out which one actually runs out.
Okay.
Better?
So the formulas are always given in moles.
Yes.
Thank you.
Chemical reactions are always balanced in terms of moles.
You just convert them to grams,
If you need to.
if you need to.
There may be problems that say, here's a mole of substance, how many moles of other substance do you make or do you use or whatever. So you just have to read carefully as to what the problem is. So now, let's see how good you are.
So,
That's the problem, is that's how good we are,
I'm sorry?
or how bad we are.
I'm doing this on purpose, because what does this look like to you?
A lot.
I think the generalized term is a mother. What I'm going to impress upon you is that this is no tougher than anything we've been doing. Because when you're doing a stoichiometry problem, how many parts of that chemical reaction are you interested in?
only
Only 2. The thing you know and the thing you want to know. Everything else is fluff.
Fluff.
And is not a problem.
This one's the fluff.
So,
I don't have space right now.
so here are the conditions. Given 15.8 grams of potassium permanganate. Oh, I should ask you what that is. What's KMNO for?
Potassium.
Potassium permanganate.
What a class. And 6.80 grams of hydrogen peroxide and excess HCl. Oh crap, here's something new.
Yeah.
Excess HCl, what does that mean?
All that HCl.
If it's excess, it means it's not the limiting reagent. So what it is a neon sign that says, ignore this. It's not a consequence.
Since there's an H2O2, would we leave the water on the other side in H2O, or would it still be easier to change it to HOH?
Well, you're not balancing, so I wouldn't change it.
Okay.
I mean, the equation's already balanced, or theoretically it's balanced as numbers. And you're asked to find out how much water is produced. Okay? In grams. So go.
Start.
Yes, you do. You have some starting materials. What are you gonna do to those gram values?
Turn some more.
Turn into moles. And then you're gonna relate the moles of one to the moles of what?
Get the smallest. Right.
Well, let's find out what we're gonna get the smallest of first.
But it's
We're relating the moles of these things to moles of,
H2O.
what we're looking for.
And it says HCl is the excess, so wouldn't it be
So
the,
HCl is ignored. It's not the limiting reagent. We don't have to worry about it.
oh, I thought that meant that it was. Okay. Maybe Sydney. Did you work that out? Could you tell me what you did? Cause I'm so confused.
Yeah. Well, page 12. Okay. We'll do that.
And then the also can.
So how is it, you see what it says, to, iron over 2 moles of aluminum?
Mm.
See, can you read it on the movie?
I'm trying to
No.
2 point something.
Grams, 2 point something.
I need help.
I know, I'm not doing that.
I don't know why. I didn't do it because I thought
Did you get it, Sydney?
Not yet.
Well, you know, the walls are
Okay, we got it.
I'm asking.
I didn't
You didn't write it.
That's the
What's the answer?
It's wrong.
Dr. Vaughn, I know that we have to move on, but can you kind of like direct me which step I need to take, step by step?
Well, you want to change the gram amounts to moles.
Right,
Okay.
so I need to have this across from that.
Right. So what's
This
that?
in a K. I thought I had to look at the ratio and then say
Not-
what's two
not-
of these.
First of all, you have to change it to moles though. Okay.
Yeah, I set
And
my
that
moles
requires
here,
using the molecular weight.
so these are canceled. Oh.
Yes,
So,
but you're saying 1 mole is 2 grams?
no,
How do you find the molecular mass?
can you,
Okay, so here's chart that there's no page to do. They've given that information.
Hold on. Why are you calculating water?
do you know how to do the, here sitting? Do you know
I
how
got it
to
wrong.
do,
I had no idea.
but do you at least know how to What is it converted from? Grams to moles?
No, I don't know if I did it right, so I don't wanna tell you. This I got wrong. He said it was wrong, like he did.
Don't leave them both hanging like that.
Okay, he did 15.8 grams KMNO4 divided by 158 grams. And
For
then
the first part with the K.
you got 0.1 moles
Yeah. You're looking
KMNO4
for water, he said. So not the
multiplied
H2O.
by 8/2.
Right.
It gives you 0.4 moles of H2O times 18 is
You got it right
7.2
here.
I'm about to get ready. Do it again. I need your rice.
Oh.
No,
Already took hers and nobody.
she didn't look like she was
No.
You did 0.2 times 8/5.
Yeah. And then that's the moles of each shirt.
So you did times 8 and then you divided by 5.
Yeah.
Could you see what that is? Yeah, but you got 0.2.
And then you change that to grams. That's the moles of each shirt.
Oh, okay. You probably, because this one's actually the lowest amount, so you have to finish this one. Like, don't stop at that one, you have to finish that part.
Right? Right?
Well, remember, these are already balanced for you. So,
What'd you get? He said your answer was wrong.
wow.
What'd you get as a gram? What gram?
7.2.
Answer? No.
Javon, no, because I don't know how to do that. I don't know how to,
I didn't see an answer.
Oh,
I
here's
don't know
the
how to
answer.
convert it.
Well, you have to use the molecular mass. To change grams
Of
into moles, you use the molecular mass. So you
of
have to go to the
potassium.
periodic table and find out how much 1 mole of this substance would
This.
weigh.
And 4 oxygen.
Right,
And then that goes here.
yes,
And then 1 mole goes here.
yes.
And since I'm going from large to small, then I need to multiply.
I don't know what that means, but
Okay.
the way you have it set up is.
So limiting reagent is
Okay, I get it now.
Is that the answer?
No. So you've got this many moles of water. Oh, water is 18. Not 32. What is it? 32. H2O. Say it loud.
Okay, we're ready to try this one?
No,
No.
Yes.
no, please.
Well, I'll go ahead and start. If you don't want to watch, don't watch.
No, because we want to pay attention.
You had to do the camera.
So our first job is to change the starting amounts to moles, okay? So we have 15.8 grams, 1 mole of KMNO4 is about 158 grams per mole. So that tells us that we have about 0.1
0.
moles of KMNO4. Now what we're really interested in is how much water can that make? So we connect that to the water using a mole ratio, looking for moles of water, knowing moles of KMNO4, and what's the ratio between these two guys and where does it come from?
So it's 8/2.
8/2 coming from the balanced chemical equation. So this is 8/2, so that tells me that I can make 0.4 moles of water. Okay? Then you do the same thing for the peroxide. 1 mole of H2O2 is what, 34 grams? So that looks like 0.20 moles of peroxide. What sweet numbers this problem is. And again, I'm not interested in peroxide as much as I'm interested in the water. So I want moles of water over moles of the peroxide. And that ratio is 8:5. So that gives us what, 0.32 moles of water. So in truth, how much water can I make?
The one at the bottom.
The smallest, the one at the bottom, 0.32. So it wants grams. I'm going to change that to grams. There are 18 grams in 1 mole of water. And I think I get 5.76 grams of water.
Correct.
Okay. You'll find a sheet on the web for some practice. You'll find problems in your book for practice. All good things for practice. Okay, there's one other idea or concept in this chapter, and that talks about reaction yields. When we do these calculations, what we're doing is assuming that everything is going to happen correctly. Everything is going to happen perfectly. All the gods are on our side, all the stars are aligned correctly, so that all that we start with makes the product. In truth, that's not what really happens in nature. There are a lot of things that can go wrong. I've watched some of you in the laboratory, and I know that you spill. You mix things with stirring rods, take them out and lay them down, and you've lost. Think of the copper experiment that you just did recently. One of the questions was, why did Charles, I think it was, get less than 100%? Did you have any problem answering that question based on your own experiences?
No.
No, we tend to lose things easily. Sometimes it's not even our fault. It turns out, and this is a little bit advanced for us, but it turns out that some chemical reactions can't go to 100% completion. They get hung up. They get involved in what's called an equilibrium process, and they can't make 100% of the product. So often what we do is we try to calculate what's called the percent yield. The percent yield tells us how much product we got compared to what it should have been if everything worked perfectly, if it were a perfect world. And the way we get that is a very simple mathematical formula. Percent yield is equal to the actual yield over the theoretical yield times 100. Now the theoretical yield is what we calculated stoichiometrically. Like I said, this calculation was based on the fact that we thought everything worked perfectly and was not a problem with anything. Now in truth, that may not be what actually happens when we do this in the laboratory. So let's say we really produced our actual yield is 3.91.
How would you know that?
You would take it and weigh it on a balance. So think of that copper experiment that you just performed. We're asking you to calculate the percent yield of copper in that experiment. Okay? And you started out with a piece of copper that you weighed, that you massed, and you ended up with some copper that you massed. And how would you find the percent yield that you got out of that experiment? If everything went perfectly, and the gods were aligned correctly, and you paid homage correctly, and so forth, we should end up with exactly the same amount of copper that we started with. But in truth, most of you probably ended up with less. In which case, we would put the actual yield, which in the case of our water problem here is 3.91 grams, over the theoretical yield, which we calculated to be 5.76 grams, and multiply by 100. And so our percent yield here would be about 67.9%. If this were a test question, then what?
How would we get the actual?
It would have to be given. If it were a test question, the problem would say something like, the amount you actually got was 3.91 grams. How much, what was the percent yield that you got?
Could it be a problem where we actually worked it out just now? And that would be our theoretical yield, you would give us actual yield, and just have to
Yes,
put it in the.
very likely. That would be the likely scenario for such a problem. Or if it were a multiple choice question, I'd give you both, the theoretical and the actual. So you didn't even have to calculate it, you just have to do this calculation.
That would be wonderful.
I'll work on it. Questions?
For chapter 5?
Chapter 5.
Did we, I know you said we didn't have to really worry about, stoichiometry like that.
I don't think he said that.
Oh, I don't think I said that. Stoichiometry is what we've been doing for the past 2 days.
Yeah, that's what cause when I came in,
Yeah.
I'll talk about it after.
Okay, we better.
Yes,
Yeah, we want to do stoichiometry.
sir.
All right, so the next move is to go on to chapter 6. Now, here's the deal. I'm not going to do all of 6. We're only going to do the parts of 6 that give us the background we need for 7. What's the truth of the matter? Chemistry is a marvelous science. It's a marvelous course. I know you all think that. But we don't have enough time to do everything in one semester. And so we have to sometimes pick and choose. And it's been our determination that for most of your careers and experiences, you will not be doing a lot of gas law stuff. And so we're not going to do the gas laws that are found in chapter 6. We're going to be doing the liquid and solid stuff, which leads to solutions, which is chapter 7, which is probably more directly related to stuff that you would be doing in your everyday lives. And so we're going to touch on things in chapter 6 that give us the background we need for chapter 7. Now, we will mention gases to differentiate them between liquids and solids. And so that you're not totally left in the dark on this particular topic, we have a laboratory that deals with gases. The lab you're doing this week, I believe, is called the atmospheric pressure experiment. And what you're going to do is you're going to create a chemical reaction that makes a gas. You're going to capture that gas, measure how much you made in the process, and then do some calculations to determine what we call the atmospheric pressure. And we'll see how good your values come out. So, in chapter 6, you should concentrate on sections 6.1 through 6.5 and 6.11 through 6.15. 6.1 to 6.5 and sections 6.11 through 6.15. And we may be going over the stuff somewhat quickly in some cases, just again to give us some background so that we do a better job in chapter 7. Because we don't have time to do gases, we really miss out on a lot. The gas laws are a beautiful piece of science. They are actually the start of modern day science. Back in the 1600s or so, before that time, chemistry was really quite random. For one thing, people didn't have large institutions where they could do this kind of work. They didn't have large companies that dealt with this kind of work. And so the chemists that wanted to pursue this were really very limited in their resources. And they ended up studying a lot of stuff that was nearby in their hometown. So they would just study with local materials. But after about 1600, what we found was that they made advances in technology. And technology meant they had glass containers. They had flasks that could hold a gas inside. because it might have a valve on the top that could close it off to the rest of the air out here. They had pumps that could move a gas from one location to another location. They had other measuring devices that could be used, thermometers and barometers and so forth, that dealt with important fractions or factions of the gas substance that was needed to be known in order to come up with a relationship. And they found lots of relationships. Don't write this down. But they had Boyle's law, which found a connection between pressure and volume. They found Charles' law, which had a connection between volume and temperature, or pressure and temperature. They found Avogadro's law, which related the amount of a gas to a substance. And they were able to put all these laws together into one neat little package called the ideal gas law. And it's known as PIV equals NERT, or PV equals nRT. And this is what we're going to use this week in the laboratory, just so you see exposure to it. And the lab manual pretty much describes it completely. There are some restrictions on the values here. We have to use a particular unit. Pressure, for example, has to be in a unit called atmospheres. Volume has to be in a unit called liters, all in order to make this relationship hold true. But it's a beautiful piece of work, and it describes gases completely for us. Unfortunately, we don't have the time to spend on gases, and we do want to get to solutions, and so we want to look at a harder look at the stuff that deals directly with solutions. And so this form of matter generally refers to as liquids and solids. The liquids and solids are substances that are encountered in solutions much more frequently. So to begin our discussion of these things, let's talk about what's called states of matter, to define what we're talking about. That's what we're talking about. Now, if we take ourselves way back, when this course started about 3 years ago, or so it seems, one of the first things we talked about were the ancient Greeks had a periodic table. And their periodic table was much simpler than our periodic table. It had only 4 elements. You remember what they were? Earth, air, wind, fire, and water. And if we look closely at that, what they were really describing were what we call the physical states of matter. They weren't describing separate elements. They were describing how matter exists under certain conditions. So, let's define those states for us very clearly today. Gases. This is matter that will assume any volume and any shape of the container that we place it in. They are easily compressed, and they can be easily expanded. The key is they do not have definite shape, they do not have definite volume. What does that mean? If I have an oddly shaped bottle, like a water bottle here, and let's assume that it's empty, and I fill it with a gas, a colored gas, okay, where do I see that gas? Everywhere throughout the bottle. In fact, it takes on the shape of the bottle. If I could take a picture and computer remove the bottle, the gas would look like the bottle. It would have the same shape as the bottle and the same volume of the bottle. And it doesn't matter what bottle I use. If I found a bigger bottle and put the same gas into that one, it would expand to fill that bottle. If I got a huge 3-liter size bottle, it would expand to fill that one, and the color would spread itself evenly throughout the entire volume of the container that I placed it in. So, gases are matter that have no definite shape and no definite volume. They will take on the shape and the volume of whatever container you put them in. Liquids, on the other hand, is a type of matter that will assume the shape of the container, but only for a specific volume. They have a definite volume. Here, look at my water bottle again. I still have some water in here. And where is the water found? It's on the bottom of the bottle. And again, if I could computer remove the bottle, what would the shape of the water look like? It would look like the bottom of the bottle. I would not have any idea what the top of the bottle would look like, but it takes on perfectly the shape of whatever bottle I put it into, but not for the entire volume, only for as much volume as I supply liquid to fill the container.
So it's definite shape, indefinite.
So it has indefinite shape, but it has definite volume.
Because if you put it in this one, it's gonna.
Okay.
The other difference between a liquid and a gas is that liquids cannot be compressed easily. We're going to find that liquid molecules are already very close together. So can I push them together more tightly with each other? No, not very easily at all. So if I were to fill this bottle, here's an interesting experiment you could try. Get a glass bottle. Won't work with plastic, but get a glass bottle and fill it totally to the brim with cold water. Screw the lid on tightly, and then take that bottle outside and put it on your deck in the sun. And what will happen? The sun will hit the bottle, it will start to warm the liquid inside. As it warms the liquid inside, liquids expand. Now, if I could compress liquids, I would guess that that bottle could hold that liquid strongly inside of itself, but it can't. What will happen is your bottle will break. So don't use a bottle that's antique or that you want to use in the future. It will break that bottle. It will crack it, and the water will leak out. Now, why do manufacturing companies fill bottles only up to here? For that very reason. Is because if they're put in a warehouse somewhere in August, the temperature goes up, that liquid can expand. If there's a little airspace there, that liquid expands into that airspace, and the gas up there is compressible. It can be squunched, it can be compressed. The liquids cannot. So if we had filled our bottles completely, giving the consumer every cent worth of bottle that they have liquid in there, we'd be having broken bottles everywhere. Yes?
I've noticed when my son, because I don't drink milk, my son ate the empty milk carton, and he'll leave just a little in there, the lid on it, and then sit there and it starts, it expands, and when I take that lid off, it's like, and it pops off. Is that
Couple of reasons that are possible. One,
milk?
if it was really cold milk to start with,
It would have been.
and you put the lid on and leave it out in the room, then it's warming up. And as it warms up, it's not so much the liquid warming up, but it's the gases, the air that's in there that's warming up, and that's expanding. Okay? When I put this bottle into a refrigerator now, I would come back and find that it's actually kind of crushed, squunched a bit, because the temperature has gone down, the pressure has gone down, the bottle is going to scrunch. The other possibility is if you leave it out long enough, the milk is going to sour. It's possible that it can give off gases. Those gases can build up a pressure which causes the carton to expand as well. Yeah. That's probably due to the temperature. Okay, let me quickly give you the solids. Solids are matter that have a specific shape and a specific volume. So a good example of a solid is a sugar cube. Now what if I put a sugar cube into the empty water bottle? What would it look like?
Well, it would dissolve.
It would look like a sugar cube. Empty water bottle. Okay? It does not take on the volume of the bottle. It does not take on the shape of the bottle. It has its own defined shape and volume. So it has definite shape and definite volume. And that's how we can tell the difference between the three different states of matter.
Sorry.
Okay, we will continue with chapter 6 on Thursday.